All right, howdy folks. So last time we were looking at some limits together. We developed, or I just kind of stated limit properties, which were all pretty straightforward. Things like if you have the limit of two things that are added together, it's the same as taking the limit of each of those things separately and adding them together afterwards. It ends up being really tedious and for what we've seen so far, not very interesting. And that's because we were looking at limits that are in the middle of continuous functions. And because of that, all of the limits are basically the same thing as just taking the value and plugging it into the function. And so that's what happens in a continuous function. We'll define continuity a little bit later on. But because of that, it hasn't been all that exciting. And I'm going to get slightly more interesting today. So we'll take a look at some algebraic examples that aren't as straightforward and have some funky things go on when you actually take the value and plug it in. So, as it says here, basically we've only done the simple ones and we'll see where it goes now. So this case right here is going to have something a little more interesting go along. And to prove that, or show that that's really what's going on here, I'm going to just take this limit and attempt to evaluate it the same way that we evaluated well, not the same way. I'm not going to use limit laws. I'm actually going to attempt to do it the fast way, which is just punching in the -2. So we have, in this case, the limit as x approaches -2 of x plus 2 over x squared plus x minus 2. All right, so if I plug the -2 into this particular statement, we would have -2 plus 2 over -2 squared plus -2 minus 2. So in the numerator, I'm going to get -2 plus 2 is 0. In the denominator, I'm going to have 4 minus 2 is 0. Now, that particular statement, 0 over 0, isn't 0. So that's kind of a hard thing to maybe believe at first. And one of the things that we have to actually be able to envision here is that this is a limit. This is not actually asking what is going on exactly at -2. If that was the case, we do get this 0 over 0, which is what we'll see later as being an indeterminate form. However, if this isn't really dealing with limits at all, 0 divided by 0 doesn't really make a whole lot of sense. So we're kind of in this weird little spot where it's not really a 0 over 0, it's something that approaches 0 over something else that's approaching 0. So how else can we describe this algebraically to make it work out a little bit better? Well, if we take a look at what's in the numerator and denominator here, we have a simple linear function up top and we have a quadratic down bottom. Now, because of all the skills we've developed over the years, we probably can take that quadratic and make it look a little bit different. So we're going to factor it. So this is going to give us two things that add together to give you 1, multiply together to give you -2. So if we take, for instance, positive x plus 2 and x minus 1, those would add to give you 1, multiply to give you -2. Great, so that's the factoring there. And in this form, we see something a little more obvious, perhaps, in terms of something we may be able to do. So I'm going to do a cancellation of the common factor that's the same in both the numerator and the denominator. Now, the thing is that if I do that, we usually have a little caveat or a little rule that goes along with cancellation of terms that if you had a 0 in the denominator, that gives you garbage. It doesn't really mean anything. This is where the limit actually kicks in and does its magic on this particular step. Because while it is something that approaches 0 over something that approaches 0, it is not actually 0 over 0, and we don't even care what happens exactly at -2 for the x value, only as we get very, very close. And as we get very, very close, x plus 2 over x plus 2, well, it's the same value. It's very small, but it's the same one. So it does cancel out, and it leaves us instead with 1 over x minus 1. At this point, we can do the kind of the speedy trick that we learned last time. If this function is continuous at -2, which it is, we may have discussed, or you might have seen before, that, actually not in Precalc B yet. So we're going to see a little bit later on for rational functions that this thing is continuous at this space. But for the time being, I'll tell you that it is. So we can just put in the -2 and get that it's 1 over -2 minus the 1 in the denominator still, which gives us -1/3. So the result being -1/3 means that if we were to assess where this particular limit would end up, then we could find that this thing should be approaching a value of 1/3. Now I'm just trying to organize myself here. I didn't pull up Desmos before I started, so just a little touch behind here, but I'm gonna do that and switch this over to my graphing scene. All right, so what I'm going to do is we're going to plot the original function, which is x plus 2, and then over x squared, x squared plus x minus 2. All right, so plus x minus 2. And now what we have is this nice little rational function, which we're going to explore later on. But we have some interesting behavior going on specifically at this value right here, which is the x is equal to 1 value, which was, when we factored it, the other one of the factors. So it was this one right here. And because of that, switch back, that one right there that I have highlighted. Going back to the graph for a moment though, if I take and kind of skim along here, and we look at what is going on specifically at this spot, when my x value, over here, x value is in -2, it actually, Desmos is pretty smart. So underneath my cursor, it's kind of small there, that says -2 undefined. Now the reason this is undefined is because there is actually no allowed value at that particular piece of the puzzle. Now, it obviously looks like it's tracking along to a nice value from this side, and it also looks like it's tracking along to a nice value from that side. And we found algebraically that that value that we're approaching looks like it's going to be -1/3. So what I'm going to do is I'm actually going to place a point at -2, 1/3, and see, -1/3, and see where it puts us. And actually, it goes in right in that hole. So we have the filled in hole, if you wish, and it definitely does approach that -1/3 value. So this method allowed us to write the original expression differently, so that when we go to evaluate the limit, we do not get 0 divided by 0 anymore. Instead, we get -1/3, which is a constant value, and it actually is the limit of that particular function as x approaches -2. All right, so going back into this stuff for a moment. So let's go down and attempt this one instead. So this is the limit, the limit as x approaches 1 of the square root of x minus 1 over x minus 1. Now, for this particular example, you can actually do it almost the same way as last time. We can factor the denominator in this case as a difference of squares. That might seem a little unnatural, since you may not recognize, or you may not think to use x as an actual squared term. So you get root x plus 1, root x minus 1. Go ahead and do that if you feel comfortable. If not, this is probably something that's a little more natural. And so if you take from Precal 11 the skill of rationalizing parts that have roots in it by using a conjugate. So in this case, the two-term piece that we want to rationalize or change up is the root x minus 1 that's currently in the numerator. If we multiply that by root x plus 1, then we have to do the same thing in the denominator instead, because root x plus 1 over root x plus 1 is just another way to say 1. It's a fancy one, but it doesn't change the value of what we have there. So since that is actually the factoring of the difference of squares, or if you multiply it all out, root x times root x is x, root x times plus 1, we'll do it this time, is plus root x. Negative 1 times root x is negative root x, and then negative 1 times positive 1 is negative 1. And that would be all over x minus 1, and I'm going to choose not to expand my denominator. And the reason why is something you'll see in just a moment. The whole purpose of doing this is so that we will find something that hopefully cancels out algebraically and gives us something that will work out for us in the end. So we'd have x minus 1 and root x plus 1 still in the denominator. Now, we have that common factor. Numerator, x minus 1, denominator, x minus 1. Again, it's a limit, so we don't care about exactly what's happening at 1, just as we get really, really close to the value of positive 1. As we get close to the value of positive 1, both of those become extremely small. Actually, if we plug the 1 in initially, it would give us that 0 over 0, and that's why we need to go further in this particular case. I should have shown you that I should have tested that in the first place. I knew that it wasn't going to work, but that doesn't mean that we shouldn't be checking every single time just to make sure it's not that it doesn't work out at that particular value. Now, if we attempt to take the limit now, we're going to have the limit as x approaches 1 of root x plus 1. So root x plus 1 is going to give me 1 over 1 plus 1, so 1/2. And again, we could pop over to Desmos for a second. And so this time, we had as an original function the root of x minus 1 over x minus 1. And so that was our original function. This is kind of what it looks like right here. It's kind of a nifty little function. Looks all well and good, except for if we explore it here, it does have a hole. Desmos is 90-some% of the time really good at placing holes where they need to go. So you can feel good about that most of the time, as you see, which is good. Obviously, this hole is approaching a value that looks really nice from both sides. Actually, if you zoom way in on that particular value, you can get as close to it as you want. It's still going to behave really nicely. It's only at the actual, and it's going to skip on me now because of the spacing. That's really unfortunate. But it's only at the value of exactly 1 that it misbehaves. So if we take we could just skim over the side. It definitely looks like 1/2. I'm going to make a point there, and just because it's helpful to make sure that that's actually the case. So that's 1 comma 0.5. And so yes, there is an actual hole at that exact value that we found was the limit of this particular function as x approached 1. So if we take a look right here, that 1/2 is exactly what we found. So this is another technique. The first one, factoring, especially useful when you have some sort of polynomial over some other polynomial. For the most part, we're going to be dealing with ones that are pretty nice. So quadratics and linears is kind of the run-of-the-mill for that sort of example. This is also another really go-to common example where you have square roots affecting something, where if you use a conjugate, the root goes away and it will simplify from there, which allows you to put in a value for that particular limit. And so that's another example. Here is another one. Could have probably put some brackets around it to make it look a little bit better. This is one of those triple decker sandwiches where you have fractions in the numerator of a fraction. So it looks pretty awful. If we were to take the 3 and plug it in here, we get 1/3 minus 1/3 is 0 over 3 minus 3, which is also 0. Because we get 0 over 0, that does mean that this is another one that just isn't working. It's approaching something small over something that's also getting small. Now, the question is what kind of rate are they both getting small? At what speed? So if one is getting small much faster than the other one, then there's going to be some kind of domination by one of these pieces, and we can just see that algebraically the same as the last two examples without really worrying about that part of it. That becomes something that's really important to think about once you get into calculus and you take a look at something called L'Hopital's rule. You'll want to remember how to deal with these limits for then, but also recognizing these indeterminate forms, which we'll talk about in just a moment, is really, really good. So the limit as x approaches 3 of 1 over x minus 1 over 3 all over x minus 3. So this is kind of what I usually think of as being the third type of algebraic example that are kind of like your base set of ones that work out quite nicely. So in this case, we have the fractions. Fractions, the only way to really change up how they look is to take the fractions that we have in the numerator and put them on a common denominator. So in order to do that, I'm going to give both of those pieces a denominator of 3x. So we would have 3x as our common denominator. I had to multiply my first fraction here by 3, numerator and denominator, in order for that to happen. And my second fraction, I had to multiply by x, numerator and denominator, for that to happen. They're still being subtracted from each other, and we're still all over x minus 3. All right, so now with the common denominator, we can take those and say 3 minus x up top over that common denominator of 3x, still all over x minus 3. All right, 3 minus x, x minus 3. Looks very similar. It's not the same thing, though. What I can do is pull a negative out of the very top piece here, and in doing so actually reverse the signs inside of that bracket. That will allow me to see that exact same term as in the bottom, or same expression of x minus 3. Now I have an x minus 3 up top. Now, one of the problems with this particular expression is a lot of students feel uncomfortable with what cancels out with what, or maybe I should say they should feel uncomfortable with what cancels out with what, but they don't really think it through in a really careful way. You can get to a place where it's automatic, and that's totally fine. You don't need to show any steps. However, the triple layer fraction is the same really as a quadruple layer fraction. Now, that sounds awful for me to say, oh yeah, don't worry, it's the 3 layer, so think of it as a 4 layer. But if you do that, dividing by a fraction is the same thing as multiplying by the reciprocal. So if I take my numerator fraction and I multiply that by the reciprocal of what was in the denominator, this is an equivalent statement to what we had written before. That means that we only have 2 layers of fraction now, and we don't have to consider what is canceling out with what. It's obvious at this point. So we can take the x minus 3 in the numerator and the x minus 3 in the denominator. They cancel out. I'm still left with a negative 1 over 3x. And at this point, I can kind of get back to the original question. What happens if I just put in a 3? Well, I don't get 0 over 0 anymore. Actually, we get negative 1 over 9. And so, as you can imagine, if we take the trip back over to Desmos here for a moment, and we try the original statement, which is 1 minus x minus 1 over 3 all over x minus 3. So we have this nice little function here, which should have an issue at positive 3, which is where we want to evaluate the limit. And of course, it's not going to give me an easy out on actually finding the 3. There it is. So at 3, it's going to recognize that this thing is undefined. And it's not quite at 0. It looked like 0 when I had backed out the graph there, but it definitely isn't at 0. And if we put in 3, comma, and we just found negative 1/9, so negative 1/9, then we get that definitely is where this function is at positive 3. So we zoom in quite a way, it's still in the right spot. We can be pretty sure that that's where it should be. It's approaching that value, the limit of the function as x approaches 3, negative 1/9. All right, so if we go back over here, so a question then, these have all been examples where the limit has existed. And so when we were looking at limits graphically, we said that the limit definitely did not have to exist. And we have a term for that where we say the limit does not exist, or the limit DNE. So algebraically, how are we going to notice when a limit actually does not exist? So the problem with the examples that we had so far are that actually doesn't occur. So if we take a look at this example right here, which is the limit as x approaches 2 of 1 over x minus 2. There's nothing I can really do to that to change the form. I have a 1 up top. I mean, I could be really weird and fancy and replace the 1 with cos squared x plus sine squared x, but that's not going to be helpful at all. It's pretty simplified, and you can imagine there's not a whole lot that I can do to maneuver around that. If I plug in the value of 2, I find 1 divided by 0. Now, 1 divided by 0 is actually a very different statement than 0 divided by 0, which is what we were having in all the other examples so far. So, algebraically, this shows up as 1 divided by 0, which is undefined. That is different from 0 divided by 0, which, as I'm going to show you on my next slide, is indeterminate. So dividing a constant value by 0, or something that approaches 0, becomes so ridiculously large, or so ridiculously large and negative, that there is no proper way to describe how large it is using real numbers. You can see that in the picture that I have right here. The fact that this thing is just going up and down as we approach that value of 2. And if we were to show the whole graph and zoom way back from it, we would see that it just gets hopelessly large in both directions. So what we can do there is say that, well, in this case, that is an undefined value. So I'm going to show you in a moment the difference, or show some examples that are indeterminate forms, or 0 over 0 like, versus things that do not exist, which are undefined, like the constant divided by 0, for instance. Those are very easy to mix up. So the limit does not exist, which is undefined, versus the limit has an indeterminate form, which is indeterminate. If we look at some indeterminate forms here, 0 divided by 0, two small values. Both of them are getting small, although there is no description in that form which one is getting smaller faster, or whether they're getting smaller at the same speed even. If they are exactly the same as they go down, it's going to give you a value of 1. If one is always double the other one, then it's going to give you a value of 2 or a half, depending on which one is the double of the other. You could get all kinds of different things happening. The denominator could get bigger so much faster than the numerator, not just double, but like a power, some sort of exponential function faster, at which case the denominator will dominate what's going on. And if it's small that it's getting, it's going to make the division become extremely large. And so you would end up actually getting an undefined answer to an indeterminate form. Indeterminate is interesting because it actually is the way that it sounds. If something is indeterminate, it means it has not been determined at this point. And in this form, you actually probably aren't going to be able to determine what's going on. We can, however, change some of these forms algebraically in order to get a picture of what's actually going on and allow us to have an avenue to analyze those limits a little bit better. So that's what we've been doing for the rest of this video, is taking certain examples like the polynomial over polynomial, or the ones that have a little bit of a radical in them, or some sort of fraction, and playing around with some techniques that basically involve factoring using a conjugate. And if you don't remember the conjugate thing, I didn't talk about it as much as I probably should have when we covered that. But when you're using conjugates to rationalize an expression that has a root in it, you're looking to have a plus b and a minus b as the two pieces. So if you currently have a plus b, you're using a minus b as the multiplying factor. If you have a minus b currently, use a plus b as the multiplying factor and go from there. Finding a common denominator in the fraction form is kind of your other method of finding out what's going on there. So I'm not going to get into all these indeterminate forms right now. The biggest ones that we are going to see are going to be of the form 0 over 0. You will see a lot more of these in other circumstances, and it could be the infinity over infinity will come up for us too, especially when we look at limits as things approach infinity, infinite limits, and there'll be some fleshing out of that sort of thing. But most of these other ones I'm going to avoid for the time being, just to simplify the process of limits. You probably come across them when you see calculus course coming up. And in a really weird sense, there are some of these that you can actually use calculus results in order to calculate the limits easier. So I had mentioned L'Hopital's rule earlier in this video. Becomes really, really instrumental in calculating some limits. And that's it for right now. So hopefully you found that to be a bit helpful. And if you have any questions, please let me know. Take care.